Number 6 is about understanding the margin of error. So if these are our predictions, our point estimates are listed for how much of a vote someone will receive, we need to understand that the margin of error says that sure, this is a likely prediction, but it's just as likely to be, in this case, 4% higher than that or 4% lower than that. And that goes for each of these predictions here. So using that knowledge, you can then answer the question about why this race is too close to call. Number 7 is about how we can be as precise as we want to be in our confidence interval if we just choose a large enough sample size. So we can look in the book and see the formula needed if we have a margin of error that we want. So we want our confidence interval to be a certain width, a certain precision, and then we want our given level of confidence. We can plug those values in the formula, in the formulas here, to calculate n, which is the needed sample size to get those measurements that we want. So I'm going to do those calculations from the formula now here in Excel. I've copied the formula here for us to refer to. A little bit different. I couldn't do the p hats for our sample proportion or the z alpha divided by 2. Those symbols are just hard to do in Excel. But there's the gist of the formula. One thing I want to start off doing is the z alpha divided by 2. So alpha would be 5% if we have a 95% confidence level. There's 5% then in the tails. So divide that by 2, and we can use this formula in Excel. Normal distribution inverse of 5% divided by 2. And it says the critical value is 1.96. So that's what I'm going to use for z. It doesn't matter if you use negative 1.96 or positive 1.96 because we will be squaring the answer. So either way, we'll end up with a positive result. So our error, the margin of error we want is just 0.01. So if I plug those values in, we start off in part A that we're using an estimate of 0.28 for our proportion. So 0.28 times 1 minus that, and then those values that we did, the 1.96 divide by 0.01 and square it. And that's how you get the sample size needed to get that level of precision. Now you can't have a sample with a partial person in it, so we would round up then. We always round up to the next whole number. So 7745 would be your answer. Now you may have noticed there was a bit of a different formula here. It said use 0.25 if we don't have a prior estimate. But it's really the same formula, just using the largest value we can get here for p times 1 minus p. And that's if we use 0.5 for our estimate. 0.5 times 1 minus 0.5, and then the same values for the other part. And just to illustrate that even further, 0.5 times 0.5, that's where they're getting the 0.25. So it's really the same formula for both of these. Just in part A, you use that estimate of 0.28, and in part B, we use 0.5 as our estimate because we don't have anything more precise. You'll notice without the estimate, our sample size needs to be quite a bit larger to get that same level of precision. For number 8 here, we're determining t-values. I recommend StatCrunch. I'll also briefly show how to use Excel. But you can go to your calculators here, and we want your t calculator. And it has a nice little graphic that shows up with it. So the area in the right tail is 0.05, 5%, 17 degrees of freedom. So you'd come down, fill in your degrees of freedom. And you want the area in the right tail to be 0.05. So you put that you want it to equal 0.05 there. And I actually have the left tail here because I have less than. We're getting the same answer by symmetry if I make it greater than. I'd want, again, to make sure that's 0.05. But then by symmetry, you'll get the same answer, just the positive version for 0.05 in the right tail. So make sure you're looking at the correct either right or left tail for each of these. For part D, it's phrased a little different. Find the critical value that corresponds to 70% confidence, and we're assuming 16 degrees of freedom. So we want to do a between then, because 70% confidence would, a visual way of picturing that is this red area should cover 70% of the distribution here. We want to find the critical values that mark each side of the distribution so that 70% of the distribution is in between those critical values. So I'm just going to do a in between and type 70% out here. And it gives me back that the critical values are the negative and positive. Here, they're the same numbers by symmetry, just the negative version and the positive, marking the 70% cutoff. 70% of the distribution is in between them, and then 30% is outside. So 15% on this side and 15% there, for a total of 30% not shaded here in red. There are formulas you can use in Excel as well if you prefer that route. I'll show you this one here. For part A, the t value in the right tail is 5% with 17 degrees of freedom. You use t dot inverse, type in the probability you want in that specific tail, and then the degrees of freedom. Now, Excel by default does the left-hand tail, so it gives me the negative back, but we know by symmetry that in the right-hand tail, then it would be this with just a positive. So that would be how you get the answer then for the t-value. Number 9 is about understanding how confidence intervals are built. The point estimate that we get from our sample is always right smack dab in the very middle of the confidence interval. So if we're given the lower and the upper bound, we could average those, and so add them up, divide by 2, and to find the number that's exactly right in the middle between the two of them. That is our point estimate for our population mean. And then the distance between that point estimate will be the same to both the lower and upper bound, how far away it is. So you can get that by subtraction. So if you take the upper bound and subtract the point estimate, you get the distance between them, and we call that distance the margin of error. This is kind of illustrated here in the book. Our guess, our point estimate for our population parameter is always right smack dab in the middle of the confidence interval. And for lower levels of confidence, our interval is a little bit tighter around that guess, and but the guess is still right in the middle. And then if we create a wider interval, so there's more possibilities within the interval, we get a higher level of confidence. But that guess, that point estimate, is still right in the very middle of our confidence interval. Number 10 is about how to properly interpret a confidence interval. So for this example, we've surveyed 700 adults in a certain country, and they were asked how many hours they worked in the previous week. And then based on those results, we build a 95% confidence interval, and we have our lower and our upper bound. So the correct way to interpret that is that we're 95% confident that the mean number of hours worked by adults in this country, so the population mean for everybody in the country, we're 95% confident that mean was between our lower and our upper bound. So what that means is, it means if we redid this process, repeated it 100 times, each time we did it, we'd go out and survey 700 different adults, get a different random sample. And so because of that, each time we did it, we would get a slightly different lower and upper bound. Our confidence interval would be different because it's always centered on the sample mean, or whatever our sample data is. So 95% of those times, though, that confidence interval will contain the true population mean for the number of hours worked by all adults in the entire country. So 95% of our confidence intervals out of every 100 will actually contain the population mean. One flawed way to interpret a confidence interval is to say there's a 95% chance that the mean, the population mean, falls within our lower, in between our lower and upper bound. And that is implying that the population mean is doing the varying, when in fact it's the interval that varies, that changes. The interval changes for every different sample that you take. Like I was saying, if you did 100 samples, you would get 100 different intervals. The intervals varying, 95 out of those 100 will contain the population mean. So we're 95% confident the mean is in between our lower and upper bound for the given interval we get from our sample. But we don't want to say there's a 95% chance the mean is in our confidence interval, because that just implies that the mean is doing the varying. The mean is in fact fixed. If we had a way to survey every single adult in the entire country, we could find out what that exact mean was. And then there would be no need for a confidence interval, because we would know what the exact mean was, so we wouldn't need to estimate it with an interval. Another flawed way to interpret a confidence interval is to use it to make predictions about individuals. It would be wrong to say that 95% of adults worked in between our lower and upper bound, because this interval is not used to make any statement about individuals. It's just an interval that's used to estimate the population mean. And the last mistake we want to avoid with confidence intervals is to kind of shift or switch the population that it is referring to or talking about. So in this example, our survey is a random sample from adults in a certain country. So our confidence interval is about the mean from all adults throughout the whole country. It would be wrong to use it in any sort of interpretation about something other than the whole entire country. So you wouldn't want to talk about the mean for adults from one particular area or another, or a different country, or anything besides what you started with, where your sample was taken from. So the interpretation should, in this case, only be about the population mean for hours worked by adults in the whole country.